This lesson is going to look very similar to the last lesson, as we're going to follow almost exactly the same code template. But this time we're going to do it with n-grams instead of the count vectorizer. So the first question, what are n-grams? The n-grams process creates a document term matrix like we saw before. Now we still have one row per text message, and we still have counts that occupy the individual cells, but instead of the columns representing single terms, like we saw in the last lesson, now they represent all combinations of adjacent words of length n in your text. So as an example, let's use the string NLP as an interesting topic. Hopefully you agree. This table shows how that would break down. In n-grams, if n equals 2, then that's called a bigram, and it will pull all combinations of 2 adjacent words in our string. So in NLP is an interesting topic, it will pull out 4 tokens. NLP is an interesting topic. When n equals 3, that's called trigrams. It'll pull all combinations of 3 adjacent words in our string. So it will create 3 tokens. NLP is an interesting, and an interesting topic. So again, when n equals 4, that's called a 4gram, and it'll pull all combinations of 4 adjacent words in our string, as you see here with these 2 tokens. So you can make n as large or as small as you'd like, and you could think of count vectorization as n-grams with n equal to 2, so it'll just pull out the unigrams. When you use n-grams, there's usually an optimal n value or range that will yield the best performance, so generally you'll tune this value to see what generates the best model. The value here is that you get a little more context around your words. Rather than only seeing one word at a time, you'll see 2 or 3 or 4. Just to tie this back to something that we talked about earlier, NLP in everyday life, Google's autocomplete uses an n-grams-like approach. So if you type natural language into Google, it knows that a very regularly used trigram starting with natural language is natural language processing. So it might suggest that as a full phrase that you'd like to search for. So let's jump into the code. And again, we're going to use the same template as last time. So we'll move pretty quickly through some of these cells. So this step, again, is just to read in the data, and it's exactly like the last notebook, along with instantiating the Porter stemmer and storing our stop words. So let's go ahead and run that. Now, on the cleaning, this is a little bit different. We have to make a slight alteration to what we were doing previously. If you remember with the count vectorizer, we had this clean text function that we have here, and it returned a tokenized list directly into the count vectorizer function. So it did it all at once, so it was handling that cleaning and tokenizing for us. With n-grams, it wants a string passed into it, so that it can look for the adjacent words in the string and chunk them together, rather than taking an already tokenized list. So all I did was add this join function in the very last step where it takes the tokenized list, checks for stop words, and then returns the stemmed version of those stop words. If you recall earlier when we removed punctuation, we had to add back this join function so that it would take each individual character and join them back together. We're doing exactly the same thing here in this last step, except now instead of joining individual characters, we're just joining tokens back together and adding the space back in between them to create a sentence. So that's the only change I made, is taking this tokenized list that we were outputting before and just restructuring it back into a string. So we're going to pass this clean text function into a lambda function and create a new column called clean text. So this is nearly the same as what we've been doing in the past. But now we just took the tokenized list and created the string out of it. So now when we run this cell, now you can see this clean text column has all the tokens from our tokenized list. It's just reconstructed back into a sentence. Jumping into the n-grams portion. N-grams will still use the count vectorizer because it's still counting the occurrences of these groups of words. So just like before, we'll call from sklearn.featureExtraction.text import count vectorizer. The first thing, if you recall, that we have to do is instantiate the count vectorizer. We're not going to use this analyzer parameter that we saw in the last section because we're not passing our cleaning function into this. We already have the final column that we need to pass directly into the count vectorizer, so we don't need that analyzer parameter to be set to anything. What we do need is we need to tell it that we're interested in n-grams. So the default for count vectorizer is for n-gram range equal to 1, 1. And what that tells the count vectorizer is we only care about unigrams. Now, if we change the second number there to 2, then it'll tell it we want to search for unigrams and bigrams. Now, if we change that second number from 2 to 3, then that tells the count vectorizer that we want to search for unigrams, bigrams, and trigrams. So again, this parameter is telling the count vectorizer the range of n-grams that we'd like to look for. For this exercise, we're only going to look for bigrams, so that'll just be 2, 2. We're instantiating this count vectorizer, and we can store it as n-gram_vect. Now, if you recall from the last lesson, what we want to do is call this n-gram vect, and we're going to do fit_transform in order to fit and then transform our data. We're going to run it on the cleaned text column that we created just up above, and we'll store that as x counts. And then, just like we did in the last lesson, we're going to go ahead and print out the shape of x counts, and then we'll print out the feature names using this get feature names method that we used in the last lesson. So if we run that, now you can see that we still have the same 5,567 rows, but now instead of the 8,000 that we saw before, you can see that there's over 31,000 columns. So that means 31,000 unique combinations of 2 words. Now in these feature names, you'll see 2-word combinations. So you'll have 150 space ppm. Let's get beyond the numbers. So you see age, gender, age how, age join. So that's just an example of the kind of features that we'd be looking at here. So now, just like the last time, we're going to jump to a smaller sample so we can actually visualize what we're looking at here. So we'll start with the sample of the first 20 text messages, and then we're going to go ahead and just copy our code down here, and we'll just change the names that we're using. So for count vectorizer, we'll still use n-gram range of 2 to 2. Now let's just change what we're storing it as to n-gram vect sample. And then again, we need to call that in the second line. So now we want to fit and transform using that new count vectorizer. And then the data frame that we want to call is not the original data frame, but data sample. And we'll store this as x counts sample. And then we want to print out that shape. And lastly, we can just grab our vectorizer and we'll get the feature names from our new vectorizer. So let's go ahead and run that one. Now, instead of over 31,000 columns, now we're back down to 198. But if you remember, that's still higher than the 192 unigrams that we saw in our last notebook. At this point, it's worth noting that using this n-gram range can end up creating a matrix with a ton of features. So if you did an n-gram range of 1, 2, so that's grabbing all the unigrams and bigrams. In our last lesson, we saw that there were over 8,000 unigrams in the full data set. And in this lesson, we saw that there are 31,000 bigrams in the full sample. So together, that's 39,000 columns that are only using unigrams and bigrams. Now imagine if we added trigrams on top of that. So just be careful with the n-grams. It's definitely worth experimenting to see both what's going to work within memory and which is going to help you generate the best model. Just like we did last time, we know the raw output is a sparse matrix, so we're going to convert it to a data frame and add the proper column headings. So again, we'll take this x counts sample, and just like last time, we need to create an array from each entry, and then we'll wrap that in pd.dataframe so that now it takes all these arrays and creates a data frame out of it. And then lastly, we'll store that as x_counts_df. And then if we want the column names, we can do the same thing that we did in the last lesson, where we'll say x_counts_df.columns. And then we want to assign the column names based on our n-gram vect sample vectorizer. And we'll call the get feature names method. And then we'll just go ahead and print out x_counts_df. So this tells us that 2005 text and 21st May occur in the very first text message, but not in any of the other text messages. And then, for instance, weigh meat right here occurs in the very last text message, but not any of the other ones. This is a brief introduction to how you implement n-grams. The value to n-grams over regular count vectorization is that it provides a little bit more context around words. And there is certainly a trade-off when you're choosing your n value for your n-grams. If you select only bigrams, then maybe that's not enough to provide useful context. But if you go all the way up to 7 grams, you're going to have a ton of features, and you'll only see the same 7 gram, in other words, the same sequence of 7 words, maybe in one text message. So in other words, what that means is every column of 7 grams would be non-zero in only one row, and you'd have a massive matrix. So n-grams can be powerful, but they require a little bit more care in implementing.